last time we were looking at real scalar fields, okay, or we were looking at Klein-Gordon theory, and we wrote down the equations of motion. Let me first remove this. So, the equations of motion, the equation of motion for this theory is okay, that is the operator you have, and this, let me even specify the fields. So, you have phi x t is equal to 0. Okay, that is the equation of motion, which we can also write as the following. So, to make the Lorentz invariance explicit, I mean it is explicit here, but notationally more clearer, I can write this as the following, okay, plus m square phi is equal to 0, okay, where del mu this is the following. So, del mu is same as, I believe this will be familiar to most of the students, and which is same as the following. You have del mu del nu eta mu nu. Okay. These all are same. Okay. And which is, if you expand, it is del 2 over del t square minus gradient square, that you can easily see. Okay. Now, when you are writing it like this, it is very apparent that the operator here, you see the operator del mu plus m square, that operator is a Lorentz scalar. You see this term has indices which are fully contracted, and if you have all the indices contracted, that object can only be a scalar. The m square is a scalar because it has no indices, it is a Lorentz invariant quantity. So, scalar and Lorentz invariant object, they mean the same thing, and the phi we are assuming to be a scalar field. Okay, that is the field we have. So, these are either this way or that way, these are the equations of motion. Okay, good. Now, like we did for the case of Schrödinger theory, we would like to write down the action which will give Klein-Gordon equations of motion. Okay, so, we want to construct that action, and let us follow that procedure which we adopted last time. So, what we do is, okay, first I am going to do it very naively without paying much attention. So, of course, I am going to make a mistake, which I will tell you what that mistake is. So, let me write down the action to be the following. So, I take the action to be dt d cube x, okay, then phi x t, I am taking the theory to be that of real scalar fields. And if you remember, here I will put the basically the left hand side of the equation of motion. So, this entire piece, right. So, that when I take a variation with respect to phi, I will get this equal to 0, okay, exactly the way we did before. So, I put here okay, and this entire thing acting on phi. Okay, so now let us look at a variation of S, and that is dt d cube x. So, I vary this first. So, this field is varied. Okay, let me put perfect. then we have this operator. Let me just write the bracket. It's understood that I have to put that operator here, plus this field phi, okay, and then we have this operator again and delta phi. So the operator now acts on delta phi. Okay, good. So here this is good, but in this case operator is acting on delta phi. So you have two derivatives of time which are acting on phi and two derivatives of space which are acting on phi, but I can use integration by parts and pull out one after another the derivatives and put on this phi. Okay, so I can transfer the derivatives to this one. So let me do that. So this part will anyway, nothing has to be done for this piece. Let's look at this one. This will become, so because you have two derivatives, every time you put a derivative you get a minus sign, so twice, so you get minus 1 times minus 1, which is plus 1, and you will get delta 2 phi over delta t square. So this derivative has now been transferred to this one, okay, minus again the same thing, this gets transferred to that, so you have, and plus m square phi square, m square phi, there is no problem. That's a constant, so it's okay, and then this gets freed up. Okay, so you see this and that, this term and this term are identical now. Okay, so if you put delta is equal to 0, then this will work only if the term here and the term there, they are identical anyway, so you can add them up. Unless this vanishes identically, okay, this cannot be satisfied. Delta is equal to 0 cannot be satisfied, which means that we have the equation of motion. Okay, which is what you had here. Okay, good, but there is something not so good here, and let's look at that part. So here is phi, then the Klein-Gaussian operator and the phi. Okay, so now what I'll do is I'll take only one of the derivatives and put on this phi. Okay, I can do that. Now when I do so, you will have, when this goes here, you get del phi over del t, and this one you still have one more derivative that acts on this phi, so you have still a del phi over del t. So you have del phi over del t times del phi over del t, but because you transferred one derivative here using integration by parts, you get a minus sign. So what you get here is minus del phi over del t whole squared, right? So let me write down the thing. So let's look at only this piece, okay, this first term. We'll not worry about these pieces right now. Okay, so if I take my naive action, which is right plus other terms which have the m square term and the gradient square term, okay, that I am omitting for now. Now if you do that, what I said in the I was showing the previous slide, transferring this derivative here, you will get dt d cube x minus, it goes, one derivative is pushed here, so it becomes del phi over del t, and you still have one derivative left, so it becomes this. Okay, and then of course you have other terms. Okay. Now this might you might have already noticed what the problem is. We have a minus sign here, okay, in the action. So if you are looking at the Lagrangian, let me write in a more familiar setting. So the Lagrangian is for this system d cube x minus del phi over del t whole squared and other terms which are really the potential terms. Okay. This is plus. Okay. Now, see, this is a kinetic term. Okay, so Lagrangian is kinetic energy minus potential energy, and the kinetic energy has to be positive. Now, this is a square, so this is always positive. But if the coefficient is negative, then the kinetic energy becomes negative, which means this is not good. Okay, let me. It's clear from what I have said, but let me nevertheless show it in slightly more detail what I am saying. Okay. So for that, what I will do is I will go from this continuum of space to discrete space. Okay. So let's see. Okay. So let's ask, what are the generalized coordinates of this theory, of this system? So what are the generalized coordinates? Well, one thing is clear, they are definitely not x. See, this x is not a coordinate at all. To describe your system, okay, you you need to specify phi. Once you specify phi over all the space, okay, then you have specified the configuration of the system. It is not the x, okay, x is not at all a coordinate. So your dynamical variable or the generalized coordinate is phi, okay. So the generalized coordinate is phi. Okay, and x is just a label. X is labels for the coordinate. So let me make this further clearer by doing the following. So instead of taking x to be the continuum space, let's take the system and put it on a lattice. Okay, so what I'll do is I'll discretize the space. So instead of x taking continuous values here and there, okay, we'll take x to we'll make x to take discrete values. I put it on a lattice, and then we'll look at the same Lagrangian again. Okay, that way it will be easier to understand what is being said. So I will discretize space. So what I am going to do is, instead of taking this as the space, I say that I have a discrete space. Okay, so this is 2 dimensions, and you can imagine third dimension, and then these squares becomes cubes. Okay, and any point if you take here, okay, this will have label I1, I2, I3. Okay, I1, I2, I3. So which, for example, here you mean you go I1 number of steps in that direction, I2 number of steps in that direction, and I3 number of steps in the z direction. And let me take the length of each of these to be h, okay, in all the three directions. Then if I am looking at this point, I can think of a cube of side h around this point. So this point is in the center of the cube, okay. So that we will remember. So there is a cube here. Now if you look at phi x t, it becomes, when you have discretized the space, so phi x t means the field at point x, and that will become field phi at point x, and that point x is now labeled as I1, I2, I3, and of course it's a function of time. Okay, good. Now I want to write down this Lagrangian in this discrete space. So d cube x, so you take a small volume element and you are integrating over it, which means you are basically summing over all the small volume elements, and each volume element d cube x will turn into h cube. Okay, that's the small volume element we have. Okay, and we are taking h to be very, very small. Okay, h is very small. It's so small that the field phi is effectively a constant within that cell. Okay, so we can ignore any variations of phi which happens within that volume h cube. Okay, so what will integral d cube x look like? It will of course become h cube, and you have to sum over all the lattice points, which is I1, I2, I3. Okay, so that's what the integral d cube x would look like in this discrete space. And then you have a del phi over del t squared, right? What does that become? It becomes phi I1, I2, I3. So that is what your point x is. I should have written here x goes to I1, I2, I3. Okay, and as I said, this is a function of time. So del over del t squared. So you see your Lagrangian is now summation over I1, I2 and I3 h cube, okay, and then delta phi square. And no, there was a minus sign. Remember that minus sign here. Okay, now this is you see now this h cube I can put in here combined with the phi, so that will be h power 3 halves, and it will become minus del over del t of h 3 halves of phi. Okay, so let me write that also. Summation minus h minus h 3 halves. Okay, okay. So you see this looks like, now if you regard the q I1, I2, I3, so that's what I am defining. I am defining q as the coordinate. which is h3 halves of phi I1, I2, I3. Okay, then my Lagrangian is, at least the first term of the Lagrangian is, so you have to sum over all the coordinates minus q dot square. Okay. So that is what I was saying, that the kinetic term here has a negative sign, which should not happen. And you see, what are the coordinates? The coordinates are the q's, and q's are just h3 half times the phi. So it's really the phi which is the coordinate. h3 half is an overall factor you are multiplying. It's a constant that you are multiplying. Okay, and of course you have to sum over all the coordinates. Okay, so this way it's very clear that the I1, I2, I3 are just the labels for the coordinate. Okay, they are not the coordinates themselves. So I1, I2, I3, when you go to continuum, they become x. So x are the labels, and the real fields or real coordinates are the phi. Okay, and this is what we have written now, and of course you have other terms. Now, the mistake that we have done is we took the action to be this thing here, but if I take instead of s minus s as the action, you still get the same equations of motion. So as far as the equations of motion is concerned, changing the sign of s will not change anything, so that we can do. So all we have to do is put a minus sign here. That minus sign will remove this minus sign, and of course it will change other signs, and then everything will be fine. Your kinetic term will be positive. So that's one thing. So I will now correct for the minus sign. So I'll put a minus sign. And the second thing which I want to do is, instead of having q dot square, I want to have half q dot square. Okay, that's the canonical normalization you have for the kinetic term. So I will have half q dot square, but that's also easy. You can multiply your action with a half or any constant. That does not change the equation of motion. Okay, so equations of motion are not changed. So I will take my this expression which I wrote earlier and multiply with minus half, and then everything is fixed. So I get dt dqx half del phi over del t squared. Okay, it had a minus sign, it's gone. Then minus gradient of phi whole squared, then minus m square phi square. Okay, if you ever worry about the relative signs, you can easily remember that the action has to be Lorentz invariant, and unless you have a minus sign here, you will not have a Lorentz scalar quantity, right? Because you have del 2 over del t square, sorry, you have del over del t and the gradient. Okay, so if you look at del mu, this, or even better, let me write it simply this way, del mu. Okay, this, when you contract with that, that's going to give you a relative minus sign, this one. Okay, let me also write it in a slightly different form, not different, but using the notation of Lorentz indices. It becomes del mu phi, this is what I was saying above, del mu phi squared phi square. Okay, so that, because that's the term which belongs to a potential term, kinetic term is in here, one of the terms is the kinetic term, and these all are potential terms. So, they come with a relative minus sign. So, that is the action that we have now, and this is what we will work with. Okay. Okay, good. Now, we have the action with in front of us. We know what the coordinates are. Okay. Now, what we should do is we should find out what the momentum conjugate momentum is. So, momentum conjugate to the phi, or more appropriately h3 halves times phi, because I am going to use discrete space to find the conjugate momentum. So, we will find out the conjugate momentum, and I think I want to also, yeah, and then we should find out what the Poisson bracket would be of that conjugate momentum which we are going to find. Okay, because then you can quantize by simply replacing the Poisson bracket by the commutator and putting the IH bar factors at the right place. Okay, so that's what we want to do. We want to find the momentum conjugates. Conjugate, and then we want to find the Poisson brackets. Okay. Now, as far as finding the conjugate momentum is concerned, you need only the kinetic piece, kinetic term, okay, because other terms do not matter. I hope we have talked about this already, but if you have q as your coordinate, then taking a derivative with respect to q dot is what gives you the corresponding momentum. So, that is what we want to do, okay, and that is easy. Our q is, so I am again going to discrete space. My q is this, where is it? Yeah. Okay. So, if I, and the Lagrangian was with the plus sign here, and a half was this. So, let us write L for my Klein-Gordon theory is half, okay, summation over I1, I2, I3, q I1, I2, I3 dot square, okay, where q is what I showed. So, let us calculate del L over del q dot. Okay. Let me simplify the notation a bit. Instead of putting all the I1, I2, I3 every time, let me define I to be this. Okay, this pair is I1 vector I. So, here I can instead simply write this, and what would that be? So, here this becomes q I dot, sorry, vector is at the wrong place, q I dot summation. Now, I should use not I, but something else, okay, j half q j dot square, okay, which is half summation over j 2 q j dot del q j dot over del q I dot. Okay. Now, this is simple, it is half summation over j 2 q j dot, and this will be a delta function, right, unless I and j are same, this is 0, and only when I and j are equal this becomes 1. So, that is delta I j. and the summation will hit only when I is equal to j. So, you get this half cancels and you get q I dot. Okay. That is good. Now, what I could have done already is or I can still do, see, I had q I to be h 3 halves of phi I 3. Okay. Let me define the conjugate momentum p I. So, here this is p I, okay, I because you have a label I here. So, p I to be h 3 half. So, this is just defining a quantity pi. Okay, it's a function of t. So, just like your coordinate, q is phi times something, some constant, your conjugate momentum is also other than this factor, it is just the pi. Okay, pi is usually called momentum density. It is called momentum density because you see this is your momentum and you are dividing by the volume of the cube. So, it is really the momentum density. Okay. So, here in this case you have 2 I 3 dot. Okay. So, that is good, that is some notation I have introduced. We have found out what the conjugate momentum is, and this turns out to be phi dot. Okay. And good. So, I can find out now something is missing, something is missing. Yeah, the something that is missing is here. I should have a h cube here, that is missing. Did I miss on the previous one? Yeah, that is why here it should have h cube. Okay, somewhere else, here also. No, that is fine, it is here. No, sorry, no, sorry, this has been already redefined, so it is fine here. Okay, all is good, fine. Okay, now let us because our q and p are canonically conjugate pairs, if you calculate the Poisson bracket you will get the following. So, if I take a q I and p j, okay, then this Poisson bracket, the fundamental bracket, will be how much? Delta I j, right, which is just a shorthand notation for the following. It is I 1 j 1 delta I 2 j 2 delta I 3 j 3. Okay, that is what is delta I j. Now, this thing I can substitute, where is it? Here, this piece. So, q I is h 3 halves phi. So, I can put here instead of q I will have h 3 halves. Okay. Then p j I can write as h 3 halves pi. So, that will again bring a factor of h 3 halves. Okay. So, it will h 3 half, and then you have q phi I 1 I 2 I 3 with pi I 1 I 2 I 3, and this Poisson bracket will be delta I j. Okay. Or you can divide by the volume on that side and write the following. I will write on the next sheet. So, I have a delta I j, I have to divide by the volume, and I have on the left Poisson bracket of phi and pi. Okay, so phi, okay, I should have been just writing phi I pi j, okay, simpler to write this way. Poisson bracket is 1 over h cube delta I j. Okay, now if I go to the continuum limit, okay, from discrete to back to our original space, and I corresponds to x and j corresponds to y. So when I am going back to the continuum limit, this will become phi of xt, that will become pi of yt, and I should figure out what the right hand side becomes. Okay, what does it go to? This one. Now it's not very difficult to realize what it is. See, if x and y are different, meaning I and j are different, then it is 0. Okay. So unless x is equal to y, this quantity here, okay, is 0. And when x is equal to y, then it has a value 1 over h cube. Okay. So let's see what it becomes in the limit h going to 0. That's the limit of going to continuum. So that is easy. Let's take 1 over h cube delta I j, and look at the following. I sum over all I or j, which let's say j, doesn't matter, okay, h cube times this. See, this is summing over all the cells. Each cell has a volume h cube and you are summing over all of them. So when you are summing over all of them, this quantity, what do you get? You get the following: h cube cancels, okay, and delta ij will hit for only when j is I, and in that case you will get 1. So this quantity which you have here in this box is something which is 0 unless x and y are same, and it integrates over, because I am summing over all the cells, it integrates over to 1, and which is what a delta function is, okay, Dirac delta function. So clearly this quantity goes over to delta cube x minus y. Okay. So we have found the Poisson bracket of phi with its canonical conjugate momentum density, and it comes out to be delta cube xy. And if you compare with what qp for any conjugate pairs, they are, let's say if it was I and j, then they would be delta ij. You see, this is what you have here is a generalization of finite number of variables or coordinates. Okay. So here in the continuum, it generalizes to this one. Okay, that's good. Let's see what else I want to say. Okay. I will give you a rather trivial exercise. It's actually there is nothing to be done. So let me just list down here. So I have found this Poisson bracket, and obviously you have the following also. So if you have phi xt with phi yt, this Poisson bracket is 0. It vanishes. If you have pi xt pi yt, that Poisson bracket is also 0. And of course you have our third one, phi xt pi yt, Poisson bracket is delta cube x minus y. Okay, that's good. Now I can, if I wish to quantize, all I have to do is promote the phi is to operator, the pi is to operators, and replace the Poisson brackets by commutators, and the commutator for this one would just become I h bar delta cube, because you have to insert I h bar delta cube. Okay, so that is what you would do. So to quantize, okay, I will, that's the prescription, right? I will replace the Poisson brackets by commutators. So what I would get, so let me, instead of phi, let me use phi hat for the operator, pi as pi hat, and the Poisson bracket will become I h bar, sorry, the commutator will be I h bar times the Poisson bracket. Okay, so that's the prescription. So what we'll get is phi hat x t phi hat y t, this commutator would be 0. Note that even though the space points are different, these are coordinates at, these are different coordinates, right? When you have x and y different, it means different coordinates, and you are of course looking at equal time commutation relation now. Okay, then you have pi x t pi y t, that they also commute, and phi x t pi hat y t I h bar times what you had for the Poisson bracket, and that was delta cube x minus y. Okay, so these are our commutation relations. Let's put them in a bracket, in a box. And because the time is same here in both the thing, these are called equal time commutation relations. Okay, that's good. Okay, we'll stop here and we'll continue further next time.